Hello, and welcome to Space for Sleep. Pluto is one of the rare worlds whose scientific story is also a human story about memory, naming, and surprise. For 76 years, Pluto was the ninth planet. It appeared on school posters, in classroom rhymes, in children's books, in planetarium shows, and in the mental map many people carried of the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. The sequence felt fixed. It felt almost natural, as if the solar system itself had arranged its identity around those 9 names. Then, in 2006, Pluto was reclassified as a dwarf planet. The object itself did not change. It did not shrink. It did not move. No mountain collapsed. No moon vanished. No atmosphere froze because astronomers voted in Prague. What changed was the category around it. The solar system had become larger and more crowded than the old list could comfortably hold. Pluto, once treated as a lonely outer planet, turned out to be one member of a much broader population of icy bodies beyond Neptune. The map had been too simple. That is why Pluto's story still matters. It is not only a story about whether something is a planet. It is a story about what happens when science improves the map, and the improved map forces us to let go of a familiar picture. People were not upset because Pluto had lost mass. They were upset because a childhood structure had been revised. A word had moved. A place in the order of things had changed. And then, in 2015, New Horizons arrived. After 9.5 years of flight, the spacecraft passed Pluto at high speed and sent back images of a world no human eye had ever seen in detail. The result was not a bland ice ball. It was a complex, active, strange, beautiful world. Mountains made of water ice, plains of nitrogen ice slowly convecting like a frozen glacier, a heart-shaped region large enough to dominate the disk, a thin blue haze around the limb, reddish organic chemistry on ancient terrain, possible cryovolcanic structures, and a moon system more dynamic than anyone had expected. For the viewer, this twist is the hook that should carry the whole episode. The old emotional story says, Pluto was a planet, and then we lost it. The better scientific story says, Pluto was a planet in an old map, and then the map expanded. When we finally arrived, Pluto turned out to be more complex than the old map ever suggested. That is more satisfying because it does not ask the listener to stop caring about Pluto. It gives them a better reason to care. The loss becomes a doorway. The demotion becomes a recontextualization. The small world becomes not smaller, but deeper. A good Pluto episode should therefore not scold the audience for loving Pluto. It should reward that attachment with a more interesting Pluto than the one they were taught. That was the great twist in Pluto's story. The debate had made Pluto seem smaller. The spacecraft made it larger. Not larger in diameter. Not larger in mass. Larger in meaning. Pluto became the proof that a world does not need to be called a classical planet to be geologically rich, scientifically important, or emotionally powerful. In fact, its reclassification helped reveal something deeper. The solar system is not a neat set of 8 or 9 objects surrounded by emptiness. It is a layered, populated system with rocky planets, giant planets, asteroid belts, Trojan swarms, comets, dwarf planets, resonant bodies, scattered objects, and a vast Kuiper Belt that preserves material from the solar system's earliest history. Tonight, we will follow Pluto from the photographic plates of Clyde Tombaugh to the vote that changed its label, from the discovery of Charon to the Kuiper Belt, from New Horizons' fast flyby to the questions that remain open. The point is not to decide whether Pluto should feel like a planet in the heart. The point is to understand what Pluto actually is. And what it is, after all the debate, is far more interesting than the simple 9th planet of memory. The discovery of Pluto in 1930 was the product of a specific astronomical prediction, a systematic photographic search, and an extraordinary piece of attention paid to a faint, slowly moving by a 24-year-old farmer's son from Kansas. The prediction came from Percival Lowell, the wealthy Boston Brahmin who had built his own observatory in Flagstaff, Arizona, and spent decades convinced that the canals he claimed to see on Mars were evidence of a dying Martian civilization. Lowell was wrong about Mars, spectacularly wrong, but he was a dedicated astronomer, and in the second decade of the 20th century, he became convinced that anomalies in the positions of Uranus and Neptune indicated the presence of an undiscovered Planet X beyond Neptune, a massive body whose gravity was perturbing the outer planets from their predicted positions. The same reasoning that had led to Neptune's discovery in 1846, working backward from orbital anomalies to predict an unseen mass, seemed applicable again. Lowell calculated a predicted position for Planet X and initiated a photographic search at his observatory. He died in 1916 without finding it. The search was eventually resumed in 1929 when the Lowell Observatory acquired a new 13-inch telescope specifically designed for the sky survey needed to find a slow-moving outer solar system object. Clyde Tombaugh, a young man with no formal astronomical training but an intense passion for astronomy and extraordinary observational patience, was hired to conduct the search. The technique was blink comparators, photographing the same region of sky on two different nights separated by a few days, then rapidly alternating between the two photographs while watching for any object that appeared to move against the background stars, which would remain fixed. A genuine solar system object at Pluto's distance would move a detectable but small amount between photographs taken several days apart, detectable to a patient, careful observer, but easy to miss in a photograph containing hundreds of thousands of background stars. Tombaugh blinked and blinked and blinked. Dozens of photographic plates, each containing hundreds of thousands of objects to examine. On February 18, 1930, examining plates taken on January 23rd and 29th, he noticed a faint point of light, at magnitude 15, far too faint for the naked eye, that had shifted position between the two plates by the right amount and in the right direction to be an object orbiting the Sun beyond Neptune. He found Planet X. The discovery was announced on March 13, 1930, chosen as the date because it was both Percival Lowell's birthday and the 74th anniversary of William Herschel's discovery of Uranus. Lowell had been searching for a large, massive body. What Tombaugh had found was, almost certainly, much smaller, but this wasn't clear for decades. The name Pluto, suggested by an 11-year-old English schoolgirl named Venetia Burney, who proposed the name of the Roman god of the underworld to her grandfather over breakfast after reading about the discovery, was officially adopted on May 1, 1930. Tombaugh's discovery was not the result of following Lowell's Planet X hypothesis correctly. Pluto is too small and too far from Neptune to have produced the orbital anomalies Lowell had identified. Those anomalies, it later turned out, were largely artifacts of measurement errors and the particular way the data was processed, not real perturbations requiring an undetected mass. Pluto was found essentially by accident, by a thorough photographic survey of the right region of sky at the right time, conducted by someone who didn't know enough to give up when the search got tedious. In this sense, the story of Pluto's discovery is less a story of theoretical prediction confirmed, as Neptune's discovery had been, and more a story of careful, systematic observational work eventually finding what the solar system actually contains rather than what theory had predicted. Tombaugh's subsequent career was defined by continued sky surveys that produced an astonishing catalog of discoveries, none as famous as Pluto, but collectively adding substantially to the inventory of the sky. There is something almost cinematic about Tombaugh's search, but it was not cinematic work. It was repetitive, cold, technical, and mentally exhausting. A blink comparator does not tell you what matters. It only alternates two images. The observer has to notice a tiny shift among thousands of unmoving points. Most of the time, nothing happens. A plate is inspected, then another, then another. Dust marks, scratches, defects in the emulsion, variable stars, and background noise can all distract the eye. A genuine moving solar system object is subtle. It has to move by the right amount, in the right direction, between two nights of observation. Tombaugh's achievement was not simply that he looked. It was that he kept looking carefully after the novelty had vanished. That is one of the quiet lessons of Pluto's discovery. Some discoveries are not born from a single flash of insight. They are born from persistence applied to a boring method until the sky yields a small exception. The exception, in Pluto's case, was a faint moving that became a planet, then a controversy, then a dwarf planet, then a world with mountains and glaciers. The object Tombaugh found was not the object Lowell expected. Lowell imagined a massive planet X. Tombaugh found something much smaller and stranger. But science is often like that. A wrong hypothesis can still motivate a search that finds something real. The explanation fails, the object remains. This makes Pluto's discovery more interesting, not less. It was not Neptune repeated. It was not a clean mathematical prediction confirmed by gravity. It was a search inspired by a flawed idea that uncovered a real outer solar system body before anyone understood the population it belonged to. The 76 years of Pluto's planetary status were years of slow, growing uncertainty about what exactly it was and where it fit in the solar system's architecture. For most of those 76 years, Pluto was a world of inference rather than imagery. Astronomers could measure where it was. They could refine its orbit. They could estimate its brightness. They could search for changes in reflected light as it rotated, revealing that its surface was not uniform. Spectroscopy could identify ices. Occultations could measure atmosphere and size. But no telescope could show a landscape. Pluto remained a point with properties that made it unusually easy to imagine. A world that cannot be seen clearly becomes a screen for expectation. Some imagined it as a tiny cold planet, some as a captured moon, some as an icy remnant, some as the last outpost before interstellar darkness. The lack of detail allowed the word planet to do much of the emotional work. Pluto was known by category before it was known by geology. This is one reason New Horizons was so important. It replaced the category First Pluto with an object First Pluto. After 2015, the question was no longer only, what kind of body should Pluto be called? It was, what are these plains? Why are there no craters here? How can nitrogen ice convect? What built these mountains? Why does Charon have a red pole? How does the atmosphere escape? What does this tell us about small, icy worlds? Those questions are better because they are about Pluto itself. Before New Horizons, many arguments about Pluto happened at a distance from the world. After New Horizons, Pluto pushed back with detail. It refused to be reduced to a word. Before discussing the orbit numerically, it helps to imagine what Pluto's sunlight is like. At Pluto's average distance, the sun is not the overwhelming disk that dominates Earth's sky. It is still far brighter than any other star, but it is small, hard, and distant. Noon on Pluto is dim by Earth standards, yet not utterly black. It is closer to a deep twilight than to the total darkness people sometimes imagine. That detail matters because Pluto is not beyond the sun in any absolute sense. It is still a solar system world, still warmed and shaped by sunlight. Just very weak sunlight spread across an enormous distance. That faint sunlight drives real processes. It sublimates nitrogen frost. It participates in methane chemistry. It helps create atmospheric haze. It changes the balance of volatile ices across seasons that last decades. Pluto is remote, but it is not disconnected. Its surface and atmosphere still respond to the star it orbits. This is one of the most interesting balances in Pluto's science. Weak energy acting for a very long time on extremely volatile materials. A little sunlight, at the right temperature, can move nitrogen. A small heat flow from the interior can convect ice. A thin atmosphere can still create haze. A distant world can still have climate. Pluto is therefore not a frozen pause button at the edge of the solar system. It is a slow machine. From the beginning, Pluto was odd. Its orbit was clearly unlike those of the other planets, highly elliptical, carrying it from roughly 30 to 49 astronomical units from the Sun over its 248-year orbit, and inclined about 17 degrees from the plane of the ecliptic where all the other planets orbit. No other planet had an orbit anywhere near this unusual. At its perihelion, its closest approach to the Sun, Pluto actually comes inside Neptune's orbit, though the two never actually approach each other closely because Pluto is in a 2 to 3 orbital resonance with Neptune, completing exactly 2 orbits for every 3 Neptune completes. The mass of Pluto was difficult to determine because determining the mass of any object requires measuring its gravitational effect on something else. Lowell had predicted a planet X of several Earth masses, and for decades there was no reliable mass measurement that could contradict this estimate significantly. Mass estimates based on assumed planetary densities and various indirect indicators placed Pluto's mass somewhere in the range of Earth's mass down to Mercury's mass over the years following discovery. The real picture began to emerge with the discovery of Pluto's moon Charon in 1978. James Christie, an astronomer at the U.S. Naval Observatory, noticed in photographs that Pluto appeared slightly elongated in a way that changed over time. The elongation was periodic, and by measuring its period, about 6 days, and comparing it with the previously known rotation period of Pluto, Christie realized he was seeing a large moon orbiting in synchrony with Pluto's rotation, with both Pluto and Charon tidally locked to each other, each always showing the same face to the other. Charon's discovery allowed the first reliable mass determination for the Pluto system through Kepler's third law, the relationship between orbital period, orbital radius, and the total mass of the system. The result was devastating for Planet X theory. Pluto's total mass, including Charon, was about 1/500th of Earth's mass, not a fraction of Earth's mass, not a few tenths, but a tiny fraction. Pluto was smaller than the Moon, smaller than Mercury, smaller than many of the moons of the outer solar system. With a mass this small, Pluto simply could not have produced the orbital anomalies Lowell had calculated. The theoretical basis for finding Pluto where it was found evaporated. Pluto was an object discovered in approximately the right region of sky because someone looked very carefully, not because it was where theory said it should be. This made Pluto's discovery more impressive in some ways. It required sustained observational effort rather than following a calculation, but it also removed Pluto from the role of confirmed Planet X. It was something else, and what exactly that something else was would take several more decades to clarify. The size of Pluto was gradually constrained through stellar occultations, measuring the precise timing of Pluto's passage in front of background stars, and then measured much more precisely by New Horizons. Pluto's diameter is about 2,376 kilometers, smaller than Earth's moon, smaller than several outer solar system moons, but large enough for its own gravity to pull it into a rounded shape. Spectroscopy was one of the first tools that made Pluto more physical and less abstract. A spectrum is not an image. It is a fingerprint of light. Molecules absorb and reflect different wavelengths in characteristic ways. So by spreading Pluto's light into a spectrum, astronomers could identify methane, nitrogen, and carbon monoxide ices long before any spacecraft arrived. This was crucial because composition tells you what kinds of processes are possible. A surface dominated by silicate rock behaves one way. A surface with volatile ices behaves another. The presence of nitrogen ice was especially important. Nitrogen is volatile enough at Pluto's temperature to participate in atmosphere surface exchange. Methane affects both surface color and atmospheric chemistry. Carbon monoxide adds another volatile component. Together, these ices mean Pluto has a climate system, even with an atmosphere far thinner than Earth's. Color observations added another clue. Pluto was reddish in places, suggesting radiation-processed organic material. Not biology, not life, not anything that should be oversold, but real carbon chemistry produced by sunlight and charged particles acting on simple molecules. That reddish material connected Pluto to Titan, Triton, and other outer solar system bodies whose surfaces are darkened by complex organics. Before New Horizons, spectroscopy could not show where all these materials were arranged in detail, but it told scientists that Pluto was chemically interesting. The flyby later turned that chemical hint into a map. The composition of Pluto's surface was determined by spectroscopy: nitrogen ice, methane ice, and carbon monoxide ice covering most of the visible surface, with darker reddish material in some regions. The surface composition was unlike anything on the terrestrial planets or the outer gas giants, more closely related to the volatile, rich surfaces of outer solar system small bodies. Pluto's early oddness was hidden partly by affection and partly by lack of context. For much of the 20th century, the solar system had a simple public architecture. For small rocky planets near the Sun, for large giant planets farther out, and Pluto, the small dark ninth planet at the edge. That arrangement was not elegant, but it was memorable. Pluto's orbit was strange, its size uncertain, its surface invisible, but because there were no known comparable objects nearby, it could remain in the planet list as an exception. Science can tolerate exceptions for a while, but when exceptions multiply, the category has to change. Pluto was an exception when it was alone. It became a clue when the Kuiper Belt appeared. This is the real conceptual shift. Pluto did not become less interesting when other trans-Neptunian objects were discovered. It became more meaningful. It stopped being a misfit planet and became the first discovered member of a new outer solar system population. Its strange orbit, icy surface, resonance with Neptune, small size, and volatile chemistry all began to make sense in a broader setting. This is why the emotional story and the scientific story point in different directions. Emotionally, many people felt Pluto had been taken away. Scientifically, Pluto had been given a family. The scientific justification for Pluto's reclassification was built over the 1990s and early 2000s as the Kuiper Belt was discovered and its population of objects was found to be far more extensive and far more diverse than anyone had anticipated. The idea of the Kuiper Belt also solved a long-standing problem about comets. Short-period comets, the kind that return on timescales less than 200 years, cannot survive indefinitely on their current orbits. Each time they approach the Sun, they lose volatile material. They shed dust. Their surfaces change. Eventually they fade, break apart, or are dynamically removed. If the solar system is billions of years old and short-period comets are temporary, there must be some reservoir that resupplies them. The Kuiper Belt provided the natural answer for many of these objects. It is a distant reservoir of icy bodies, some of which can be nudged inward by gravitational interactions and become comets. The more distant Oort cloud supplies many long-period comets, but the Kuiper Belt and related scattered populations are central to understanding the shorter-period comet supply. Pluto, then, belongs to the same broader outer solar system architecture that feeds some of the comets we see from Earth. The frozen bodies beyond Neptune are not irrelevant leftovers. They are part of a continuing exchange between distant storage and inner solar system visibility. A comet crossing the inner solar system may be, in a sense, a messenger from a region Pluto helped make famous. The The Kuiper Belt had been theoretically proposed long before it was observed. Gerard Kuiper, the astronomer whose name it bears, suggested in 1951 that the primordial disk of material from which the solar system formed might extend beyond Neptune, populated by icy planetesimals that had never been gathered into a planet. Kenneth Edgeworth had made a similar suggestion in 1943, and some astronomers prefer the name Edgeworth-Kuiper Belt in recognition of his priority. The theoretical motivation was elegant. The solar system's architecture made physical sense only if there was a reservoir of material beyond Neptune from which short-period comets could be continuously resupplied as existing comets were depleted. The first Kuiper Belt object beyond Pluto and Charon was discovered in 1992 by David Jewett and Jane Liu using the University of Hawaii's telescope at Mauna Kea. The object, designated 1992 QB1 and later named Albion, was a dark, reddish body about 150 kilometers across orbiting at about 44 astronomical units. It was too small and too faint to have any chance of being confused with a planet, but its orbital characteristics, beyond Neptune, in the same broad region as Pluto, in a nearly circular prograde orbit, were exactly what a Kuiper Belt object should have. After 1992 QB1, the discoveries accelerated. Survey programs with increasingly sensitive cameras and systematic sky coverage found Kuiper Belt objects in the dozens, then hundreds, then thousands. By the early 2000s, it was becoming clear that Pluto was not an isolated oddity orbiting beyond Neptune, but a member, arguably the largest known member, though not for long, of an extensive population of icy bodies in the outer solar system. The Kuiper Belt was real, and Pluto was part of it. The crisis for Pluto's planetary status escalated with the discovery of Eris. In 2005, Michael Brown, Chad Trujillo, and David Rabinowitz at the California Institute of Technology announced the discovery of an object designated 2003 UB313, later named Eris. From initial measurements, Eris appeared to be slightly larger than Pluto, making it potentially the 10th planet. The discovery made international headlines and forced a confrontation with the question that had been building for over a decade. If Pluto is a planet, what makes Eris not a planet? And if Eris is a planet, are there more out there, and where does the planet list end? Michael Brown, who calls himself the man who killed Pluto, has described the moment of Eris's discovery as the beginning of the end for Pluto's planetary status. He and his collaborators were finding large Kuiper Belt objects at a rate that implied, if discoveries continued, a solar system with potentially dozens of planets. That prospect, dozens of planets, with the list growing every few years as survey technology improved, was scientifically untenable. Either a definition of planet had to be established that could accommodate Eris without ballooning the planet count indefinitely, or the existing list had to be restructured. The International Astronomical Union, the organization responsible for official astronomical nomenclature, convened a special committee and eventually brought a definition to a vote at its 2006 General Assembly in Prague. The process was contentious, the politics were complicated, and the final vote, taken on August 24, 2006, by a small fraction of the total IAU membership, many of whom had already left Prague when the vote was held, produced a new definition that has remained controversial ever since. The IAU defined a planet as a body that orbits the Sun, has sufficient mass to be roughly spherical under its own gravity, and has cleared the neighborhood of its orbit, meaning its gravity is dominant in its orbital zone, with no other large bodies sharing its orbit in ways that haven't been gravitationally settled. Pluto fails the third criterion definitively. It shares its orbital zone with thousands of other Kuiper Belt objects, many of them in or near the same orbital resonances. It has not cleared its neighborhood. By the IAU definition, It is a dwarf planet, a new category created specifically to accommodate Pluto, Eris, and similar objects. The reclassification was scientifically reasonable and conceptually defensible, but the execution, a late-session vote at an international conference attended by less than 4% of the IAU's membership, adopting a definition with significant technical problems that planetary scientists continue to debate, left lasting controversies. Alan Stern and David Levison, among others, have proposed alternative definitions, and the debate about what constitutes a planet remains active in the planetary science literature. What is not debated is that Pluto is a remarkable and scientifically important world, regardless of its category. And the best evidence for that came from the mission launched to study it. The word cleared is often misunderstood. It does not mean that a planet's orbit contains no small bodies. Earth shares its region with near-Earth asteroids. Jupiter shares space with Trojan asteroids. Neptune has resonant objects in its gravitational influence. Clearing the neighborhood means something more dynamical. Over the age of the solar system, a planet must be massive enough to dominate its orbital zone, either by accreting nearby material, scattering it away, or controlling it gravitationally in stable relationships. By that measure, Earth dominates its zone. Jupiter overwhelmingly dominates its zone. Neptune dominates its zone even though Pluto crosses inside Neptune's average orbital distance, because Pluto is controlled by a stable resonance with Neptune rather than being a rival of comparable dynamical influence. Pluto does not dominate the Kuiper Belt. It is large and important, but it shares the region with many other icy objects. It is one member of a population, not the gravitational master of a cleared orbital neighborhood. This does not make the IAU definition perfect. The definition has real problems. It applies only to bodies orbiting the Sun, which makes exoplanet definitions awkward. It creates the odd phrase, dwarf planet, which sounds like a kind of planet but is formally not counted as one under the IAU wording. It emphasizes dynamical environment rather than geophysical complexity. Planetary scientists who prefer a geophysical definition argue that a planet should be any world massive enough to become round under its own gravity, regardless of whether it has cleared its orbit. Under that definition, Pluto, Ceres, Eris, Europa, Titan, and Earth's moon would all be planetary bodies. This is why the debate persists. It is not simply nostalgia versus science. It is partly a question of which property matters most, orbital dominance or intrinsic world-like complexity. For a sleep documentary, the useful answer is not to turn the debate into a fight. The useful answer is to see what the debate reveals. The solar system can be organized in more than one scientifically meaningful way. If the question is dynamical architecture, Pluto is a dwarf planet in the Kuiper Belt. If the question is geology, atmosphere, moons, surface processes, and internal evolution, Pluto is absolutely a world. The launch itself carried a certain urgency because Pluto was moving away from the Sun. Pluto had reached perihelion in 1989, its closest point to the Sun, and by the time New Horizons launched it was already receding. As it moved outward, there was concern that its atmosphere might begin to freeze out onto the surface. No one knew exactly how quickly that would happen or how long the atmosphere would remain accessible to study. Waiting too long might mean arriving at a Pluto with a much thinner or partially collapsed atmosphere. This gave the mission a scientific clock. It was not just a matter of wanting to get there eventually. There were atmospheric reasons to go while Pluto was still in a favorable part of its long season. The mission also had to reach Pluto while enough sunlight illuminated the encounter hemisphere and while Earth geometry allowed communication. Outer solar system missions are always constrained by time, but Pluto's atmosphere made the timing feel particularly important. A world with a 248-year orbit does not offer human-friendly schedules. New Horizons was fast partly because it had to be. The spacecraft crossed the Moon's distance in hours, flew past Jupiter for a gravity assist, then spent most of a decade crossing the dark. Even at that speed, reaching Pluto required patience on the scale of a childhood. New Horizons was launched on January 19, 2006, about 7 months before the IAU vote that reclassified Pluto. The timing produced one of the more ironic sequences in recent space history. The first mission to Pluto was launched while Pluto was still officially a planet, reached it after it had been demoted to a dwarf planet, and returned images so extraordinary that the question of its classification seemed, to many observers, almost surreally beside the point. The New Horizons spacecraft is roughly the size and shape of a baby grand piano and weighs about 479 kilograms. New Horizons was not large, but it was carefully concentrated. The spacecraft carried 7 science instruments. LORRI, the Long-Range Reconnaissance Imager, provided the sharpest black and white images. Ralph combined color imaging and infrared spectroscopy, allowing the team to map surface composition and color. Alice, an ultraviolet spectrometer, studied Pluto's atmosphere by looking at sunlight and starlight passing through it. REX, the radio experiment, used changes in the spacecraft's radio signal to probe atmospheric pressure and temperature. SWAP and PEPSSI measured charged particles and the interaction between Pluto's escaping atmosphere and the solar wind. The Student Dust Counter, built by students, measured dust impacts across the outer solar system. That instrument set was chosen for a flyby, not an orbiter. It needed to gather global context, high-resolution close-up imaging, atmosphere measurements, particle data, and composition maps during a fast pass. The spacecraft had to turn between targets, manage limited onboard storage, keep itself warm, point its antenna back at Earth, and survive far from the Sun on nuclear power. One small but important detail is that New Horizons could not transmit its data quickly. At Pluto's distance, even with the Deep Space Network listening, the data rate was tiny. The spacecraft stored encounter data on board and sent it back over many months. That meant the scientific discovery continued long after the encounter date. New images and measurements arrived slowly, like messages from a place already receding into the dark. This slow return shaped public experience too. Pluto was not revealed in one day. It was unfolded. It carries 7 instruments, including 2 cameras, the Long-Range Reconnaissance Imager for high-resolution imaging and the Multispectral Visible Imaging Camera for color and wider field imaging, along with ultraviolet and infrared spectrometers, radio and plasma instruments, and a student-built dust counter. Power comes from a single radioisotope thermoelectric generator, the same technology that powers the Voyager spacecraft, producing about 200 watts at launch and declining slowly over time. New Horizons launched on an Atlas V rocket modified to carry an additional upper stage booster, giving it more velocity than any spacecraft since Voyager 1 and 2. It departed Earth at a heliocentric velocity that made it the fastest spacecraft launched in history at that time, fast enough that it crossed the Moon's orbit in just 9 hours, compared to the 3 days Apollo required. A Jupiter gravity assist in February 2007, close approach on February 28, 2007, at a distance of about 2.3 million kilometers, provided an additional gravitational kick that shortened the transit time to Pluto by approximately 3 years. The Jupiter flyby was also a rehearsal. New Horizons was built for one encounter that could not be repeated, so the Jupiter system became a chance to test instruments, tracking, data handling, and encounter operations on a real planetary target. The spacecraft observed Jupiter's atmosphere, rings, magnetosphere, and moons. It imaged volcanic activity on Io, watched lightning and cloud motion on Jupiter, and collected data that were scientifically useful in their own right. This matters because a spacecraft is not only a machine. It is an operating system in the broadest sense. Hardware, software, navigation, teams, schedules, command sequences, deep space network time, data pipelines, and people who have to understand how all of it behaves under pressure. Jupiter gave the team a way to practice before Pluto. After that, the spacecraft entered long hibernation periods. Hibernation sounds peaceful, but it was also practical. Electronics age. Systems consume power. Human teams cannot operate at encounter intensity for 9 years. By letting New Horizons sleep for long stretches, the mission reduced wear and allowed the spacecraft to cruise through the empty years between planets with only periodic wake-ups. There is a strange patience in that. A spacecraft launched with enormous speed spends most of its journey asleep. It crosses hundreds of millions, then billions, of kilometers in silence, carrying a planned future encounter inside its memory. When it finally woke for Pluto, it was not arriving at a familiar target. It was arriving at a world still largely unknown. During the Jupiter flyby, New Horizons returned the most detailed images of Jupiter's volcanic moon Io taken since the Galileo spacecraft's demise, including dramatic images of an active volcanic eruption in progress. After Jupiter, New Horizons entered a hibernation mode. Most systems powered down to reduce wear and power consumption for extended periods during the long cruise through the outer solar system. Mission controllers woke the spacecraft periodically for instrument health checks, trajectory corrections, and science observations. But the bulk of the transit years were spent with the spacecraft largely asleep. The science team spent those 9 years refining their knowledge of Pluto's system using the best available Earth-based and Hubble observations, planning the observation sequences for the encounter, and training on the spacecraft's characteristics and limitations. The system they would be visiting turned out to be more complex than originally known. Nix and Hydra were found in Hubble images in 2005, before New Horizons launched. Kerberos was found in 2011 and Styx in 2012 during later Hubble searches for additional moons and potential hazards, debris rings, or small objects that could threaten New Horizons' approach. Each discovery required additional planning to ensure the spacecraft's trajectory and observing sequence remained safe. The final approach to Pluto began in January 2015, when New Horizons cameras began to resolve Pluto as more than a point of light for the first time. Those approach images were a rare kind of suspense in modern astronomy. For decades, Pluto had been a disk only in the most technical sense. Hubble could see brightness patterns, but not a world in the way people imagine worlds. As New Horizons approached, the pixels became geography. A bright patch became a heart. A dark belt became named terrain. A point of light became a rotating object with recognizable regions. This gradual sharpening gave the encounter an almost emotional rhythm. It was not like opening one photograph. It was like watching a fog lift over a place that had been known by name for 85 years but never seen clearly. By the time closest approach arrived, the world had already begun to reveal its character. It was not smooth. It was not uniform. It was not simple. Pluto was announcing its complexity before the highest resolution images had even arrived. The approaching images immediately showed something unexpected. Pluto was not the featureless, uniform world of the best prior Hubble imagery. It had large-scale contrast, bright and dark regions that resolved into a complex surface as the resolution improved week by week through the spring and early summer of 2015. Closest approach to Pluto occurred on July 14, 2015. New Horizons came within about 12,500 kilometers of Pluto's surface, moving at 14 kilometers per second. In those few hours, it gathered more data about Pluto than had been accumulated in the 85 years since its discovery. The images and data it returned transformed the scientific community's understanding of what Pluto was. The speed of the New Horizons flyby is one of the details that gives the mission its tension. New Horizons did not go into orbit around Pluto. It could not. Slowing down at Pluto would have required a large propulsion system and a much heavier spacecraft. Instead, it flew past at roughly 14 kilometers per second, gathering its most important observations during a narrow window of hours. The spacecraft had one chance to photograph the encounter hemisphere, one chance to measure the atmosphere by watching the Sun and Earth pass behind Pluto, one chance to map Charon and the small moons from close range, one chance to do everything it had spent 9.5 years traveling to do. Because the spacecraft was so far from Earth, the flyby could not be controlled in real time. The entire encounter sequence had to be programmed in advance and executed automatically. The spacecraft turned from target to target, moved its instruments, stored data, and continued through the system without waiting for Earth to confirm each step. When closest approach occurred, mission controllers could not know immediately whether the spacecraft had survived. They had to wait for the signal that came later. That waiting was part of the drama. New Horizons flew through the Pluto system, did its work, and only afterward turned back toward Earth to say that it had survived. The first post-encounter signal was not a picture. It was a health check, a message that the spacecraft was alive, oriented, and carrying the data. The images came slowly after that. The full data set took more than a year to return because the spacecraft was so far away and the downlink rate so low. Pluto did not arrive all at once. It arrived piece by piece. A sharper disk, then a heart, then mountains, then haze, then Charon's canyons, then small moons, then composition maps, then atmospheric profiles, then data subtle enough to keep scientists busy years later. That slow arrival made Pluto feel newly discovered more than once. One of the reasons this complexity landed so strongly is that it contradicted a very reasonable expectation. Small bodies lose internal heat faster than large bodies. Pluto is small. It orbits far from the Sun. Its surface temperature is extremely low. A simple prediction would be that it should be old, cratered, and mostly inactive, a frozen archive rather than a moving system. Many bodies in the outer solar system do preserve ancient surfaces. Callisto, for example, shows a heavily cratered record of early solar system bombardment. It would not have been absurd for Pluto to look like that. Instead, New Horizons found sharp contrasts between old and young terrain, between cratered dark regions and smooth bright plains, between rigid water ice mountains and mobile nitrogen ice, between haze-filled atmosphere and frozen surface chemistry. The surprise was not one feature. The surprise was the combination. That combination matters for retention because it gives the episode an intellectual mystery. How does a world this small, this cold, and this distant remain active enough to renew its surface? The answer is not a single mechanism. It is the interaction of internal heat, volatile ices, insulating layers, seasonal cycles, impact history, and the peculiar physics of materials at Pluto temperatures. Pluto is interesting because it should have been simpler. The New Horizons images revealed a world of startling geological complexity and visual drama. The most immediately striking feature in the first high-resolution images was a vast, bright region in the shape of a heart, stretching across much of Pluto's near side. The heart became famous because it looked emotional, but its real power is scientific. Tombaugh Regio is not a sentimental marking. It is an active volatile system. Its bright surface is dominated by ices that are mobile at Pluto's temperatures: nitrogen, carbon monoxide, and methane. These ices can sublime, flow, recondense, and participate in a climate cycle. The left lobe, Sputnik Planitia, is not simply bright terrain. It is a vast reservoir of nitrogen ice, probably several kilometers thick in places, lying inside a basin that may have shaped Pluto's rotation. The heart also affects the atmosphere. Studies have suggested that Sputnik Planitia can drive winds as nitrogen ice sublimates and recondenses, effectively making Pluto's heart beat through the atmosphere. This is not a heartbeat in a biological sense, of course, but it is a striking physical link between landscape and climate. A bright nitrogen plane can help move gas around an entire world. There is something beautiful in that precision. The feature that looks most symbolic is also one of the most physically important regions on Pluto. It is not merely a heart in appearance. It is a center of activity. This is the kind of discovery that makes Pluto memorable for viewers. It gives the mind an anchor, a heart-shaped glacier on a distant dwarf planet, slowly turning over under weak sunlight, helping shape the atmosphere of a world almost 40 times farther from the Sun than Earth. This feature, roughly 2,000 kilometers across, is now called Tombaugh Regio, after Pluto's discoverer. In its left lobe, a smooth, bright plane named Sputnik Planitia is the most scientifically extraordinary feature on the entire surface. Sputnik Planitia is a roughly oval basin about 1,000 kilometers across, filled with nitrogen ice to a depth that remains uncertain but is estimated at several kilometers. The nitrogen ice is not smooth. It is organized into a complex pattern of polygonal cells, typically ranging from 10 to 40 kilometers across, with slightly raised rims and slightly depressed centers. These cells are the surface expression of convection, the slow overturn of nitrogen ice driven by heat from Pluto's interior, with warmer, less dense ice rising in the centers of cells and cooler, denser ice sinking along the edges. The convective cells are visually similar to the convection cells visible on the surface of the Sun, though operating at temperatures around -230 degrees Celsius rather than thousands of degrees. The convection in Sputnik Planitia implies that heat is escaping from Pluto's interior, that Pluto is not geologically dead. The source of this heat is likely the decay of radioactive elements in the rocky core, the same process that heats Earth's interior, but in a much smaller body. The heat flow is small, far less than Earth's, but sufficient to drive very slow convection in the nitrogen ice over timescales of hundreds of thousands to millions of years. Sputnik Planitia also shows how a surface feature can influence an entire body's orientation. If a basin fills with dense nitrogen ice, it changes the distribution of mass on the dwarf planet. Over time, a rotating body can reorient so that heavier or dynamically favored regions move toward more stable positions relative to the spin axis and the tidal relationship with a companion. In Pluto's case, Sputnik Planitia's location near the anti-Charon point has been interpreted by some models as evidence of true polar wander, the whole outer shell of Pluto shifting orientation after the basin became filled with ice. This is a large idea hidden inside a beautiful image. The bright heart-shaped region is not just lying on Pluto. It may have helped move Pluto's crust relative to its interior. The possibility of a subsurface ocean enters this discussion because a liquid layer can make reorientation easier and can affect the gravity and stress patterns associated with the basin. Again, this is not proof of an ocean, but it shows how geology, rotation, orbital dynamics, and internal structure become tied together. Pluto is small, but the questions it raises are planetary in scale. Sputnik Planitia is thought to occupy an ancient impact basin, a large crater formed early in Pluto's history that has since been filled with nitrogen ice that migrated there from other parts of the surface over geological time. The basin likely formed early in Pluto's history, when the bombardment rate was higher, and its location, roughly antipodal to Charon, may reflect a true polar wander event in which the added mass of the ice-filled basin caused Pluto's rotational axis to shift so that the basin settled near the equator facing away from Charon. To the west of Sputnik Planitia, the terrain changes dramatically. A chain of mountains, informally named Al-Idrisi Montes, Tenzing Montes, and Hillary Montes, the latter two after the first men to summit Everest, rises to heights of 3 to 4 kilometers above the surrounding plains. These mountains are made not of rock, but of water ice. Pluto's bedrock is water ice, at temperatures around minus 230 degrees Celsius. Water ice is as hard and rigid as rock and serves the same structural role. The mountains of Pluto are ice mountains, but they are genuine mountains, tectonically formed features that speak to forces within Pluto's interior that pushed and deformed the icy crust. The origin of these mountains remains somewhat uncertain. Tectonic compression, possible cryovolcanic intrusion, or other processes have been invoked. The water ice mountains are important because they reveal a hidden inversion of ordinary experience. On Earth, nitrogen is a gas in the air, methane is a gas we burn, carbon monoxide is a dangerous gas, and water ice is fragile enough to melt in your hand. On Pluto, the roles are rearranged. Nitrogen, methane, and carbon monoxide can behave as surface ices that migrate and flow. Water ice becomes bedrock. It is so cold that water ice is rigid, strong, and rock-like, able to support mountains kilometers high. This reversal helps the listener feel Pluto as a genuinely alien environment rather than simply a colder version of Earth. The familiar materials are there, but they do not behave in familiar ways. The chemistry has been moved into a different temperature regime, and the landscape follows from that. A mountain made of water ice on Pluto is not a snow pile. It is a mountain of frozen bedrock. A nitrogen plain is not a puddle. It is a glacier. Methane frost is not a trace gas. It is a landscape material. Understanding Pluto means letting go of Earth temperature instincts. That is one reason the New Horizons images were so surprising. The eye sees mountains and plains in dark regions, and the mind reaches for Earth analogies. But the physics underneath is different. The surface is made of substances we know, acting under conditions we never experience. What is clear is that they are geologically young features, relatively little modified by subsequent bombardment, consistent with the broader picture of Pluto as a world with ongoing or geologically recent geological activity. In other regions of Pluto, especially near the equatorial terrain east of Tombaugh Regio, New Horizons revealed bladed terrain, long, sharp ridges hundreds of meters high, thought to be made largely of methane ice. These features may form through long-term cycles of methane frost deposition and sublimation, somewhat analogous to penitence on Earth, but operating on a far larger scale, in a colder environment, and over much longer timescales. The dark reddish terrain covering much of Pluto's equatorial and southern regions is composed of complex organic molecules, tholins, a word coined by Carl Sagan to describe the dark, orange-red material produced when simple organic molecules like nitrogen, methane, and carbon monoxide are processed by ultraviolet light or charged particles. The names on Pluto also matter because they turn remote geography into something humans can discuss. Tombaugh Regio honors the discoverer. Sputnik Planitia honors the first artificial satellite and the beginning of the space age. Tenzing Montes and Hillary Montes recall the first confirmed ascent of Everest. Cthulhu Macula draws from mythic darkness. Charon itself, the ferryman of the underworld, fits the name Pluto with almost theatrical precision. These names are not the science, but they help the science become memorable. A map is not only coordinates. It is a way of returning to a place in thought. There is also something fitting about Pluto's geography being named with a mixture of science, exploration, mythology, and underworld imagery. Pluto was never an ordinary world in the public imagination. Its surface names reflect that mixture: discovery, darkness, myth, voyage, ice, and surprise. Tholins coat the surfaces of many outer solar system bodies, including Titan, and are of significant astrobiological interest as precursors to more complex organic chemistry. Pluto's dark regions are rich in tholins, giving the planet, dwarf planet, its characteristic reddish-brown appearance in color images. Pluto's seasons are extreme not because its tilt is Earth-like, but because the geometry is complicated and slow. Its orbit is highly elliptical. Its rotational axis is tilted dramatically. Its relationship with Charon locks one hemisphere toward the large moon. Over decades, different regions receive sunlight at very different angles and for very different durations. Polar regions can experience long periods of darkness and illumination. Volatile ices respond by sublimating, moving, and condensing. This is climate without oceans, forests, rain, or breathable air. It is climate written in frost. On Pluto, a season can alter where nitrogen ice is stable. It can change atmospheric pressure. It can affect haze production. It can brighten or darken regions depending on frost deposition and sublimation. Because the year is so long, the full seasonal cycle is impossible to observe in a single human lifetime, which makes every occultation and every long-term measurement valuable. This is also why Pluto remains scientifically active after the flyby. New Horizons gave one extraordinary snapshot. Earth-based observations continue the time series. The world keeps moving through its season whether a spacecraft is there or not. The distribution of Pluto's surface materials reflects complex seasonal and long-term volatile transport processes. Nitrogen, methane, and carbon monoxide ices all have different vapor pressures and respond differently to changes in solar illumination as Pluto moves through its highly elliptical orbit and its rotational and orbital geometry changes over time. The result is a surface in a state of continuous, slow rearrangement, with volatile ices sublimating from sun-facing regions and recondensing in shadowed or cold regions, driven by climate cycles on timescales from the 12,000-year precession cycle of Pluto's axis to the 248-year orbital period. One particularly striking feature is the bladed terrain, regular, sharp ridges of methane ice rising hundreds of meters, found near Pluto's equator. These features have no exact analog on any other known solar system body. They form through a process of methane frost accumulation and sublimation driven by Pluto's long day-night cycle and axial orientation, and they represent one of the more unusual geological landforms yet discovered anywhere in the solar system. The dark polar region, formerly named Cthulhu Macula, is one of the oldest-looking regions on Pluto, heavily cratered and covered in dark tholins, suggesting an ancient surface not recently reshaped by nitrogen ice deposition. The boundary between Cthulhu Macula and the bright Tombaugh Regio region is sharp and dramatic. The transition from dark, ancient terrain to bright, geologically young terrain is one of the most visually striking boundaries on any world in the solar system. Sputnik Planitia is the center of modern Pluto science because it is almost impossible for a small, cold body to have a feature that active unless something interesting is happening. Nitrogen ice is soft compared with water ice at Pluto temperatures. Over long timescales, it can flow. The polygonal cells seen across Sputnik Planitia are interpreted as convection. Warmer nitrogen ice rises slowly, spreads, cools, and sinks again along cell boundaries. This is not a fast process. It is glacial in the deepest sense, but it means Pluto is transporting heat from its interior through a volatile ice layer today or in the geologically recent past. The plane is also remarkably young in crater counting terms. Impact craters accumulate over time. A surface with many craters is generally old. A surface with few craters has been renewed. Sputnik Planitia is nearly crater-free in New Horizons images, suggesting that the surface is being refreshed on timescales far shorter than the age of the solar system. That single fact changed Pluto. Before New Horizons, many expected a frozen relic. After New Horizons, Pluto became a place where surface renewal, volatile transport, glacial flow, and possible internal heat all had to be explained. The basin may also connect to a possible subsurface ocean. Some models suggest that Sputnik Planidea's location and mass distribution are easier to explain if Pluto has, or once had, a liquid water layer beneath its ice shell. The evidence is not a direct detection. No spacecraft has measured an ocean under Pluto. But the idea is taken seriously because the geology, gravity-related reorientation models, and thermal evolution can point in that direction. If Pluto does have a buried ocean, it would be a remarkable reminder that liquid water may be possible far beyond the classical habitable zone, not because sunlight is warm there, but because ice, antifreezes, radiogenic heat, and insulation can preserve internal reservoirs for very long times. Pluto would not be habitable in the easy surface sense, but it would be part of the broader family of ocean world questions that includes Europa, Enceladus, Titan, Triton, and other icy bodies. This is how one feature, the bright left half of a heart-shaped region, became a window into the interior of a world at the edge of the planetary system. Occultations are one of the most delicate ways astronomers studied Pluto before any spacecraft arrived. When Pluto passes in front of a distant star, the star does not simply blink off like a light behind a solid wall. If Pluto has an atmosphere, the starlight fades gradually as it passes through the thin gas, bends, and is absorbed or refracted. By measuring that fading from different places on Earth, astronomers can infer pressure, temperature, and atmospheric structure. This is an elegant method because it turns a chance alignment into a probe. A star behind Pluto becomes a flashlight. Earth becomes the detector. The atmosphere, almost unimaginably thin, leaves its signature in the way the starlight disappears and returns. Occultations showed that Pluto had an atmosphere before New Horizons reached it, and continued occultation campaigns after the flyby remain important because they track changes over time. A spacecraft flyby gives detail. Occultations give continuity. For a world with seasons longer than human lives, continuity is precious. The atmosphere of Pluto, thin, primarily nitrogen with traces of methane and carbon monoxide, was known from Earth-based stellar occultation measurements before New Horizons arrived, but the spacecraft's observations transformed understanding of its structure, composition, and behavior. At surface level, Pluto's atmospheric pressure is about 10 to 12 microbars, roughly 100,000 times thinner than Earth's atmosphere. Despite this extreme tenuousness, the atmosphere has a measurable structure and dynamics. New Horizons found that Pluto's upper atmosphere extended to greater heights than expected, with neutral gas detectable far above the surface and atmospheric escape occurring more slowly than some early models predicted. The visible haze layers themselves were concentrated much lower, rising hundreds of kilometers rather than thousands. The atmosphere shows distinct haze layers, blue in color when Pluto is backlit by the sun, produced by the same tholins forming photochemistry that darkens Pluto's surface. These hazes are visible in dramatic backlit images taken by New Horizons as it looked back toward the sun after closest approach, showing Pluto's thin blue atmospheric haze illuminated against the black of space in a way that makes the planet look, for a moment, almost Earth-like. The blue color comes from small haze particles scattering shorter wavelengths of sunlight more efficiently, similar in spirit to the scattering that makes Earth's sky blue, though occurring in a far thinner, colder, chemically different atmosphere. Pluto's atmosphere is not stable over long timescales. As Pluto moves closer to the Sun through perihelion, surface ices sublimate and the atmospheric pressure increases. As it recedes toward aphelion, temperatures drop, nitrogen condenses back onto the surface, and atmospheric pressure may decrease dramatically. Some models and occultation observations suggest that Pluto's atmospheric pressure can decline substantially as it recedes from the Sun, though exactly how far and how quickly it collapses remains a subject of ongoing study. The specific behavior depends on poorly constrained parameters about the thermal properties of Pluto's surface and the dynamics of volatile transport, and represents one of the key scientific questions that ongoing analysis of New Horizons data and future observations aim to address. The escape of gas from Pluto's atmosphere was measured by New Horizons and found to be occurring at a rate somewhat lower than earlier models had predicted, suggesting that the atmospheric escape is somewhat less efficient than simple models had assumed, possibly because the escaping gas forms a corona around Pluto that partially shields the lower atmosphere from direct solar wind erosion. Pluto's atmosphere is especially strange because it is both fragile and global. On Earth, weather is driven by thick air, oceans, sunlight, rotation, and complex surface exchange. On Pluto, the atmosphere is far thinner, the sunlight much weaker, and the surface ices themselves are part of the climate system. Nitrogen frost can sublime into gas, travel through the atmosphere, and recondense elsewhere. Methane and carbon monoxide participate in the same volatile cycle in different ways. The atmosphere is therefore connected directly to the migration of ice across the surface. The blue haze seen by New Horizons is not a sign of breathable air. It is a sign of photochemistry. Ultraviolet light breaks apart methane and other molecules high in the atmosphere. The fragments recombine into more complex hydrocarbons and nitriles, forming tiny haze particles that slowly settle downward. Over time, radiation processing can darken these particles into tholin-like material, contributing to the reddish colors on the surface. This is one of the most elegant cycles on Pluto. Gas rises, sunlight changes it, haze forms, particles fall, surface chemistry changes, and then volatile ices move again with the seasons. Pluto's atmosphere also became a surprise after the flyby because it was colder and more compact in the upper atmosphere than some pre-encounter models expected. That colder structure helps reduce atmospheric escape. Before New Horizons, some models suggested Pluto might be losing atmosphere in a more comet-like flow. The spacecraft showed a slower, more restrained escape. Even here, Pluto resisted the simple version of the story. Charon, Pluto's enormous moon, large enough relative to Pluto that the system is sometimes called a double dwarf planet, was revealed by New Horizons as a geologically complex world in its own right, with features that are surprising and in some cases still incompletely understood. Charon is about 1,212 kilometers in diameter, roughly half of Pluto's roughly 2,376 kilometer diameter. Its surface is predominantly water ice, darker and less reflective than Pluto's bright nitrogen ice regions, with a significant dark polar region in the north, Mordor Macula, that has no clear analog on any other body in the solar system. Mordor Macula's dark, reddish-brown color is thought to be produced by a remarkable process. Pluto's escaping atmosphere, nitrogen and methane gas, leaving Pluto and moving through the space between the two bodies, is captured by Charon's gravity at the North Pole, which during Charon's winter is in prolonged darkness. The captured gases freeze onto the cold polar surface as methane frost. When sunlight eventually returns after the decades-long polar winter, the methane frost is processed by ultraviolet light and energetic particles, converting it to tholins. As the nitrogen and methane eventually sublime away during the polar summer, the tholins remain as a dark, persistent residue. The polar cap of Charon is effectively painted by chemistry, colored by the chemistry of Pluto's escaping atmosphere, captured and processed on Charon's surface over long timescales. Charon may be quieter than Pluto today, but it may preserve an older drama more clearly. If Charon once had a subsurface ocean, that ocean eventually froze. Water expands when it freezes. Inside a small icy body, that expansion can crack the outer shell, opening great chasms and extensional features across the surface. The huge canyon system seen by New Horizons may be the scar of that freezing, a global-scale memory of internal change. This makes Charon a kind of fossil ocean world. It may not have liquid water now, or if it does, the evidence is far less direct than for more active moons. But its surface may record the time when its interior changed state. A frozen ocean can leave geometry behind that is scientifically valuable because it shows that ocean world evolution is not limited to currently active moons. Some worlds may carry the ruins of oceans that no longer exist. Others may preserve liquid layers deep beneath ice. The outer solar system contains many stages of this story. Charon is not merely Pluto's companion. It is a chapter in icy world evolution. Charon's geological history reveals past activity more dramatic than its present-day frozen surface suggests. A vast canyon system, Argo-Chasma, cuts across much of Charon's equatorial region, a rift structure implying that the moon's interior expanded at some point in its history, stretching and cracking the surface in a way consistent with the freezing of a subsurface ocean. If Charon once had a liquid interior ocean, possibly shortly after its formation by the giant impact thought to have created the Pluto-Charon system, the freezing of that ocean would have expanded the volume, forcing the surface to crack and rift. The resulting canyon system could be tens of kilometers deep in places, dwarfing Earth's Grand Canyon and making it one of the largest canyon systems in the solar system. The Pluto-Charon system is thought to have formed by a giant impact early in the solar system's history, analogous to the Earth-Moon system's formation. The giant impact idea also helps explain why the Pluto system feels like a miniature planetary system rather than a single isolated dwarf planet. A collision between Proto-Pluto and another large Kuiper Belt body could have produced a disk of debris. From that debris, Charon formed, and perhaps the smaller moons as well. The result was not a simple captured moon, but a family shaped by one ancient event. The orbits of the small moons, their brightness, their irregular shapes, and their strange rotations all belong to that family history. The comparison with Earth's moon is useful but not exact. The materials were colder, icier, and farther from the sun. The scales were smaller. The dynamical environment was different. But the principle is familiar. A violent beginning can produce a stable companion system that lasts for billions of years. In Pluto's case, the violence of formation led to one of the most graceful orbital arrangements in the solar system. Two locked worlds facing each other across space, with smaller moons moving around the pair. A large object, perhaps Ceres-sized or larger, struck the Proto-Pluto, and the debris from both bodies coalesced into the Pluto-Charon binary. The impact would have been energetic enough to melt the interior of both bodies, potentially producing the subsurface oceans whose subsequent freezing left geological scars on both surfaces. The four small moons, Styx, Nix, Kerberos, and Hydra, orbit the Pluto-Charon system in approximately circular orbits at distances of roughly 40 to 65,000 kilometers from the center of mass. The small moons add a surprising layer of motion to the Pluto system. A viewer might imagine tiny moons moving calmly around the central pair, but New Horizons revealed that some of them rotate chaotically. They do not keep one face pointed neatly toward Pluto and Charon. They tumble. Hydra, in particular, was found to rotate rapidly and unpredictably compared with a simple tidally locked moon. This chaos comes from the gravitational environment. Pluto and Charon form a binary, and the small moons orbit around both. The changing gravitational torques from the central pair can disturb their spin states. Their irregular shapes make the effect stronger. The result is a moon system that is not only visually complex, but dynamically rich. The small moons are also unusually bright, probably because their surfaces are rich in clean water ice. That brightness contrasts with the darker reddish surfaces of Pluto and Charon. Again, the system resists simplification. One dwarf planet, one large moon with a red pole, and four smaller bright, irregular moons, all connected by a violent origin and long-term gravitational evolution. The Pluto system is not just Pluto. It is a miniature outer solar system family. Their sizes range from roughly 15 kilometers to roughly 50 kilometers, and their surfaces appear to be predominantly water ice, far brighter than Pluto or Charon. The small moons have complex rotation states. New Horizons observations confirmed that at least Hydra tumbles chaotically, rather than maintaining a stable orientation under the combined gravitational torques from Pluto and Charon. They are thought to have formed from debris ejected in the same giant impact that created the Pluto-Charon binary, rather than being separately captured objects. The Pluto-Charon relationship is one of the most distinctive in the solar system. Charon is so large compared with Pluto that the barycenter, the center of mass around which both bodies orbit, lies outside Pluto itself. Pluto and Charon do not behave like a large planet with a tiny moon in the familiar Earth-Moon sense. They behave more like a binary system, each locked to the other, turning together every 6.4 Earth days. If you stood on the Pluto-facing hemisphere of Charon, Pluto would hang in almost the same place in the sky, large and unmoving. If you stood on the Charon-facing side of Pluto, Charon would do the same. This mutual lock gives the system an almost intimate geometry. The same faces always look at each other. The small moons orbit farther out, influenced by the combined gravity of the central binary. Their chaotic rotations are not just curiosities. They are consequences of living in a gravitational environment where the central mass is not a simple point. Charon also matters because it provides contrast. Pluto is volatile-rich, bright in places, dark in others, with nitrogen and methane moving across its surface and atmosphere. Charon is more water ice-dominated, less volatile, and geologically different. Together, they show how two bodies formed in the same impact and orbiting the same region can evolve into very different worlds. The dark polar cap on Charon is one of the most poetic pieces of chemistry in the Pluto system. Material escapes Pluto, travels through space, is cold trapped on Charon's winter pole, processed by sunlight, and left behind as reddish residue. Charon is literally marked by Pluto's escaping atmosphere. A moon painted by its primary world is the kind of detail no telescope from Earth could have revealed. Pluto in context, its place in the Kuiper Belt and its relationship to other trans-Neptunian objects, is as scientifically important as its individual properties, and the New Horizons mission has illuminated this broader context as well. The Kuiper Belt now contains more than 2,000 confirmed objects with well-characterized orbits, and statistical modeling suggests the true population of objects larger than 100 kilometers is roughly 100,000. The Kuiper Belt also changed the emotional scale of Pluto. Before the belt was discovered, Pluto felt like the last marker before darkness. It was the final bead on the string, the outermost named place in the simple planetary order. After the belt was discovered, Pluto became a doorway. Beyond Neptune was not empty. It was populated by icy remnants, resonant bodies, scattered objects, binaries, contact binaries, red surfaces, volatile ices, and the frozen record of planetary migration. The belt is not merely a collection of leftovers. It is evidence that the early solar system was more violent and more mobile than the old, orderly picture suggested. Neptune did not simply form where we see it and sit still forever. The giant planets likely migrated, scattering small bodies, trapping some into resonances, ejecting others toward distant orbits, and leaving behind a structure that still records those ancient gravitational rearrangements. Pluto's 2 to 3 resonance with Neptune is part of that record. It is not a random orbit. It is a fossil of planetary migration written in orbital timing. Every 2 Pluto orbits correspond to 3 Neptune orbits, a rhythm that protects the 2 bodies from close encounters despite Pluto's path crossing inside Neptune's average distance from the Sun. Pluto's orbit looks dangerous on a flat diagram. Dynamically, it is stable because of resonance. That is another way Pluto became more interesting after it lost planet status. It stopped being merely the end of a list and became evidence for the history of the outer solar system. The belt's population can be divided into several dynamical subclasses based on orbital characteristics. These dynamical subclasses are not just labels. They are clues. Cold classical Kuiper Belt objects tend to have low inclinations and relatively undisturbed orbits. They may preserve material that formed near where it still orbits. Their colors, binaries, and fragile structures make them especially valuable as fossils of the early outer solar nebula. Hot classical objects, scattered disk objects, and resonant objects tell different stories, often involving Neptune's migration and gravitational scattering. This means the Kuiper Belt is not a smooth ring of debris. It is a structured archive. Its objects remember where the giant planets moved, how Neptune captured resonances, how small bodies were scattered outward, and how some populations avoided the strongest disturbance. Pluto belongs to the resonant population called Plutinos. That name is one of the clearest signs of Pluto's new role. It is not merely an object in the Kuiper Belt. It is the namesake of an orbital family. Other bodies share its 2 to 3 resonance with Neptune, and the family itself helps scientists reconstruct the migration history of the outer planets. Again, the demotion story becomes too small. Pluto did not lose importance. It changed from a final planet into a reference object for an entire class. The classical cold Kuiper Belt objects, with nearly circular, low-inclination orbits representing material that formed approximately in place and has never been strongly perturbed. The classical hot Kuiper Belt objects, with more eccentric and inclined orbits, thought to represent material scattered from the inner solar system during the giant planet orbital reshuffling of the NICE model. The scattered disk objects, with highly eccentric orbits extending to very large distances, and the resonant objects, locked in mean motion resonances with Neptune. The Plutinos, which like Pluto are in a 2 to 3 resonance with Neptune. Pluto is the largest known Kuiper Belt object by diameter, while Eris, which belongs to the scattered disk, is slightly more massive. The two are close enough in size that Eris forced the classification crisis, but the current best picture is that Pluto is a little larger and Eris is a little heavier. Makemake, Haumea, Quaoar, Sedna, and dozens of other large Kuiper Belt objects complete the population of the largest known bodies. After its Pluto flyby, New Horizons was approved for an extended mission to a more distant Kuiper Belt object. The target selected, after an extended search using the Hubble Space Telescope, was a small classical Kuiper Belt object designated 2014 MU69 and later named Arikoth, a word from the Powhatan language meaning sky, in the dialect of the indigenous people of the mid-Atlantic region of the United States. New Horizons flew past Arikoth on January 1, 2019, at a distance of about 3,500 kilometers, making the most distant planetary flyby in history at about 44 astronomical units from the Sun. Arikoth is a contact binary, two lobes that formed separately and then gently came together in a low-velocity merger. Each lobe is roughly 15 to 20 kilometers in diameter, and the combined object is roughly 36 kilometers in its longest dimension, shaped like a reddish snowman or gourd. The contact binary morphology and the very gentle nature of the merger, confirmed by the lack of any deformation or damage at the contact point between the lobes, suggested that the two components came together at very low velocity, perhaps a few meters per second, rather than in a violent collision. This gentle merger is thought to be characteristic of how planetesimals formed in the outer solar system, not through violent hit-and-stick collisions, but through the slow gravitational collapse of pebble clouds in the early solar nebula, with the two components of the binary forming separately within the same cloud and then slowly and spiraling to merge. Arrokoth also helped correct the mental scale of the Kuiper Belt. Pluto is large and spectacular, so it naturally dominates attention. But most Kuiper Belt objects are not Pluto's. They are smaller, darker, colder, and more numerous. They are planetesimal remnants rather than dwarf planets. Studying one small object up close helped balance the picture. The Kuiper Belt is not only about its largest members. It is about the building blocks. Arrokoth's smooth, gently merged shape suggests a low-speed origin that preserves early structure rather than a history of violent reshaping. Its reddish color and methanol-bearing surface are clues to outer solar system chemistry. Its lack of obvious major disruption suggests that some cold classical objects have remained relatively undisturbed for billions of years. In that sense, Arrokoth may be less dramatic than Pluto, but more primitive. Pluto shows what a large icy body can become. Arrokoth shows what a small icy building block can preserve. Together, they make New Horizons more than a Pluto mission. They make it a Kuiper Belt mission. The color and surface composition of Arrokoth, uniformly reddish, with methanol ice detected by New Horizons spectrometers, is representative of the classical cold Kuiper Belt, the most primitive and least processed material accessible in the solar system. Arrokoth is, in a meaningful sense, one of the most pristine solar system objects ever examined up close, a fragment of the original solar nebula preserved in the deep freeze of the outer solar system for 4.5 billion years. Arrokoth is important because it is quieter than Pluto. Pluto is large enough to have geology, volatile cycles, an atmosphere, and a complex satellite system. Arrokoth is small, cold, ancient, and comparatively simple. That simplicity is its value. It appears to preserve information about the way planetesimals assembled in the early solar system, before collisions, heating, and geological processing erased the original structure. The gentle contact binary shape argued against a violent build-up model for at least some outer solar system bodies. The two lobes did not smash together at high speed. They came together softly, likely after forming within the same collapsing cloud of pebbles. This supports the idea that planetesimals can form through streaming instability and gravitational collapse, a process in which small solid particles concentrate in the solar nebula until their collective gravity brings them together. This matters because planet formation begins with a difficult step. How do tiny dust grains become kilometer-scale bodies quickly enough before drift, collisions, and gas drag remove them? Arrokoth provides a fossil clue. It is not a planet, not a dwarf planet, not geologically spectacular in the way Pluto is, but it may preserve a shape from the birth of planetesimals themselves. New Horizons, therefore, gave us two different outer solar system lessons. Pluto showed that small icy worlds can be active and complex. Arrokoth showed that small primitive bodies can preserve the gentle assembly of the solar system's building blocks. New Horizons' mission continues. By 2026, the spacecraft was roughly 9.5 billion kilometers from Earth, far beyond Pluto, after its longest hibernation period so far. A radio signal from that distance took nearly 9 hours to reach Earth. NASA and the New Horizons team have continued using it for heliophysics, dust, Kuiper Belt, and outer solar system observations, with the spacecraft expected to have enough power for operations into the 2030s if its systems remain healthy. It is not another Voyager yet. It has not crossed the heliopause, but it is traveling outward through the same vast outer frontier and will keep adding measurements from a region few spacecraft have ever reached. A Pluto orbiter would be a very different mission from New Horizons. New Horizons was a scout. It flew fast, saw one hemisphere in high detail, sampled the atmosphere during one brief geometry, and moved on. An orbiter would become a resident observer. It could watch the same surface features under changing light. It could revisit Sputnik Planitia. It could map the far side properly. It could fly repeatedly past Charon, Nix, Hydra, Kerberos, and Styx. It could measure gravity more precisely and perhaps test interior models. It could watch the atmosphere over seasons rather than hours. But orbiting Pluto is difficult because the spacecraft arrives too fast. Every kilometer per second of speed has to be removed somehow. Chemical propulsion requires fuel, and fuel adds mass, and mass makes launch harder. Electric propulsion works slowly and needs power. Aero capture at Pluto is tempting in theory, but very hard because the atmosphere is thin and variable. Mission designers have studied creative options, including using Charon's gravity for orbital tours or combining flybys with propulsion strategies, but none is simple. This is why Pluto's next chapter may take time. The science case is strong. The engineering is hard. The budget competition is real. The distance is unforgiving. Pluto rewards patience because it demands it. The future of Pluto exploration, returning to Pluto with a mission capable of orbiting and studying it over years rather than hours, has been discussed in the planetary science community since shortly after the New Horizons flyby revealed how much there is to see. An orbiter mission to Pluto would be extraordinarily valuable. New Horizons imaged only about 50% of Pluto's surface at its best resolution. The planet's far side was not illuminated during the approach phase, and only partially resolved during departure. An orbiter could map the entire surface at high resolution, follow seasonal changes in the volatile ice distribution over years, study the atmosphere continuously rather than in a single encounter, and track geological changes, if any occur, on observable timescales. Multiple flybys of Charon and the small moons would provide more comprehensive characterization of those worlds than New Horizons' single pass could deliver. Getting an orbiter to Pluto faces formidable engineering challenges. The journey takes roughly 9 to 10 years. Slowing down from interplanetary cruise velocity to orbit insertion requires carrying fuel for propulsion, dramatically increasing the spacecraft mass, or using an innovative technique like aero capture, using Pluto's tenuous atmosphere for aerobraking to reduce velocity, which faces its own technical challenges given how thin Pluto's atmosphere is and how uncertain its exact properties are at the time of arrival. The power requirement for an orbiter operating at Pluto's distance, where solar panels provide negligible power, requires a radioisotope power source of the type that has faced production and procurement challenges in recent years. The Planetary Science and Astrobiology Decadal Survey of 2023 to 2032 placed high priority on exploration of the ice giants, Uranus and Neptune, and on Mars sample return, while acknowledging Pluto and the Kuiper Belt as scientifically important targets for future study. This prioritization is not a rejection of Pluto. It is a reflection of mission scarcity. Outer solar system missions are expensive, slow, and technically difficult. A spacecraft sent to Pluto or the Kuiper Belt requires radioisotope power, long cruise time, complex navigation, and decades of commitment. Space agencies have to choose between many worthy targets: Mars samples, Europa, Enceladus, Titan, Uranus, Neptune, comets, asteroids, Venus, lunar science, and heliophysics. Pluto competes in that crowded landscape. But the scientific case for returning to Pluto remains strong. New Horizons showed a hemisphere in detail, not a whole world over time. It revealed activity, but could not monitor change. It measured atmosphere once during one seasonal state. It flew past Charon and the small moons without the repeated close passes that an orbiter could provide. The best argument for a Pluto orbiter is simple. The flyby made Pluto too interesting to leave alone forever. Still, the timescale will likely be long. A return mission would require patience on the scale of decades. Pluto has already taught astronomy to think slowly. A dedicated Pluto orbiter mission concept has been studied in preliminary form, but the financial and technical investments required make it a longer-term prospect rather than an imminent development. There is also the question of timing. Pluto's seasons are long. One orbit takes 248 Earth years. A human mission planner cannot watch a full Pluto year in a career or even in several lifetimes. That means every spacecraft encounter captures only one seasonal chapter. New Horizons saw Pluto in the years after perihelion, while its atmosphere and volatile deposits were in a particular state. A future orbiter would see another chapter, not the whole book. This makes long-term Earth-based occultation studies valuable. When Pluto passes in front of background stars, astronomers can measure changes in its atmosphere by watching the starlight dim and bend. These observations extend the time baseline beyond the spacecraft flyby. They help track whether the atmosphere is expanding, cooling, or declining as Pluto moves farther from the Sun. A future orbiter would connect those remote hints to direct measurements. It could watch frost migrate, haze change, pressure shift, and seasonal patterns evolve. Pluto's climate is slow, but slow does not mean static. In the nearer term, continued analysis of the New Horizons dataset, which took more than a year to transmit in full from Pluto's distance at the low available data rate, is still producing scientific results. Papers continue to appear characterizing the geology of Sputnik Planidea's convective cells, the composition and history of the dark tholin-rich terrain, the dynamics of Pluto's atmosphere, and the properties of the small moons. The New Horizons mission, long over in the sense of having left Pluto behind, is still scientifically productive in ways that will continue for years. A Pluto orbiter would also answer questions New Horizons could not even frame completely. Is Sputnik Planidea still changing? Do nitrogen glaciers flow measurably over years or decades? How does Pluto's atmosphere respond as the dwarf planet moves farther from the Sun? Are there active surface atmosphere exchanges we could watch in real time? Does Charon's surface preserve more evidence of a frozen ocean? Are the small moons shaped mainly by the ancient impact, by later collisions, or by tidal evolution in the binary system? What is hidden on the hemisphere New Horizons saw only poorly? The most important limitation of New Horizons is not that it failed. It is that it succeeded so well during such a brief encounter that it revealed how much a longer mission could do. An orbiter would turn Pluto from a flyby target into a world with weather, seasons, maps, repeat imaging, and time domain geology. That is the difference between glimpsing a place and living with it as a subject. For now, Pluto remains a world known in a single brilliant pass. To hold Pluto clearly, it helps to set it beside a few other worlds. Ceres, in the asteroid belt, is also a dwarf planet, but it is rocky and icy, much closer to the Sun, with bright salt deposits and evidence of brines. Eris is farther and more massive than Pluto, colder and more distant, with a moon of its own. Haumea is elongated and rapidly rotating, surrounded by a ring and moons. Makemake is bright, methane-rich, and another large Kuiper Belt body. Triton, now Neptune's moon, may be a captured Kuiper Belt object and looks in some ways like Pluto's larger cousin, with nitrogen frost, a thin atmosphere, and geyser-like activity observed by Voyager 2. This comparison shows that dwarf planet is not a small or boring category. It is a category full of different histories. Some dwarf planets are in the asteroid belt. Some are in the Kuiper Belt. Some scattered objects travel far beyond. Some have moons. Some may have had oceans. Some preserve ancient surfaces. Some show volatile cycles. Pluto is the most famous, but it is not the whole story. That is exactly why the reclassification mattered. It opened the door to a richer taxonomy of small worlds. The solar system is not made only of major planets and debris. Between those extremes are worlds large enough to become round, complex enough to have geology, and numerous enough to change how we understand planetary formation. This is why Pluto works so well as a long-form space story. It begins with a simple emotional hook. We lost the 9th planet. But the real reward is that the loss opens into a richer picture. The viewer does not have to choose between nostalgia and science. The best version of the story gives both. The remembered Pluto of childhood and the actual Pluto of mountains, glaciers, haze, chemistry, moons, and Kuiper Belt context. That combination is what keeps the episode from becoming a dry classification debate. It gives the listener a reason to care before the science begins, and then gives the science enough depth to justify the emotion. Let's take a moment, finally, to think about what Pluto actually is, not in the category theory sense that exercised the IAU and the public in 2006, but in the deeper sense of what kind of world it turns out to be. Pluto is a world of extraordinary geological complexity for its size and position. It has mountains of water ice 3 kilometers tall. It has a basin of nitrogen ice the size of a small continent, slowly convecting like a pot of warm porridge. It has seasons driven by a 248-year orbit and an axial tilt that has shifted significantly over geological time. It has an atmosphere, thin but real, blue and hazy in backlit images, that condenses and sublimes with the seasons. It has a large moon in synchronous orbit and a family of smaller moons tumbling chaotically in the gravity field of the binary. It has organic chemistry, tholins, complex enough to color its surface red-brown and potentially to include molecules relevant to prebiotic chemistry. It is not the dead, featureless rock ball that most scientists expected before New Horizons arrived. It is a living world, in the geological sense, a world where processes are ongoing, where the surface is changing on timescales of centuries to millions of years, where the interior is still warm enough to drive slow convection in the ice above it. The word living here has to be used carefully. Pluto is not alive. There is no evidence of biology on its surface. Its atmosphere is too thin, its surface too cold, and its chemistry too radiation processed for anything like surface habitability. But in planetary geology, a world can feel alive when it is not static. It can have cycles, renewal, transport, internal heat, volatile exchange, and landscapes that change. By that standard, Pluto is alive in the same way a glacier is alive, or a dune field, or a frozen moon with cracks and resurfacing. It moves without intention. It changes without awareness. It has processes. That distinction matters because it keeps the wonder honest. Pluto does not need speculation about life to be extraordinary. Its actual geology is enough. Whether it is a planet or a dwarf planet does not change any of this. The debate about its classification is real, and the scientific and linguistic issues are genuine. But Pluto's properties are what they are regardless of the box we put it in. A world with mountains and glaciers and organic chemistry and a complex moon system and an escaping atmosphere and convecting nitrogen plains is remarkable, whether you call it the 9th planet or the first of many dwarf planets or a representative Kuiper Belt object. The older schoolroom diagram also hid the fact that the solar system has zones rather than just planets. There is the inner rocky planet region. There is the asteroid belt, which is not a failed planet exactly, but a population shaped by Jupiter's gravity and early solar system dynamics. There are the giant planets, each surrounded by rings, moons, and magnetospheres. There are Trojan populations sharing planetary orbits. There are centaurs crossing between giant planets. There is the Kuiper Belt beyond Neptune. There is the scattered disk reaching onto more elongated orbits. Far beyond, there is the distant Oort cloud, inferred from long-period comets. Pluto belongs to this zoned architecture. It is not simply after Neptune. It is part of a region with its own structure, history, and dynamical fingerprints. Once that is understood, the 8-planet list becomes less like the whole story and more like the largest landmarks on a much richer map. This is the version of the solar system that modern viewers deserve. Not simpler, but more beautiful because it is more populated. What Pluto's demotion did accomplish, regardless of its scientific merit, was to begin a reconceptualization of the solar system structure that is genuinely important. The solar system is not 8 or 9 well-defined planets orbiting in clean isolation. It is a complex, populated system with 2 rocky planet zones, 2 giant planet zones, multiple asteroid populations, several cometary reservoirs, and an extended outer region of icy bodies numbering in the hundreds of thousands of objects we know about, and perhaps millions we haven't found yet. Pluto helped prompt this broader reconceptualization, and in that sense, in being interesting enough and strange enough to force a rethinking of categories, it served science well. The man who found Pluto, Clyde Tombaugh, died in 1997, 9 years before its reclassification and 18 years before New Horizons flyby. The presence of Tombaugh's ashes aboard New Horizons gives the mission a rare circularity. The man who found a point of light never saw the world it represented. Decades later, part of him passed that world in a spacecraft carrying instruments capable of revealing mountains, haze, glaciers, and moons. This detail could feel sentimental if it were invented. It is powerful because it is real. It also captures a deep truth about exploration. Discovery is often unfinished by the discoverer. Tombaugh opened a door he could not walk through. New Horizons walked through it for him. In the only way machines can walk, by flying past, measuring, recording, and sending the evidence home. There is a quiet dignity in that. A human being notices a faint moving dot. A civilization remembers. A spacecraft is launched. The dot becomes a world. The discoverer's ashes pass by the discovered place. Then the spacecraft continues outward, beyond Pluto, towards smaller and colder remnants of the solar system's beginning. Pluto's story is full of categories and debates, but this part is simple. Someone looked carefully. Something was found. And many years later, we finally saw it. His ashes were placed in a small container aboard New Horizons before launch. On July 14, 2015, Tombaugh's ashes crossed the closest point to the world he had spent months of patient, careful work to find. In a technical sense, his remains became part of the first spacecraft to visit Pluto, and they are now, with the spacecraft, traveling outward through the Kuiper Belt toward the edge of the solar system. Tombaugh never knew what Pluto was. He found a faint moving dot in a photographic plate, called it Planet X, and spent the rest of his life associated with it without ever having close access to what it actually looked like, or what it was made of, or what was happening on its surface. That detail gives the story a human quietness that is easy to miss. A person can discover something without knowing what it really is. Tombaugh found the point. Later generations found the context. New Horizons found the world. Science often works like that. One generation locates the mystery, another names the pattern, another sends the instrument, another interprets the data. Pluto's story stretches across all of those generations. Lowell's mistaken Planet X, Tombaugh's patience, Christie's discovery of Charon, Jewett and Lou's Kuiper Belt, Brown, Trujillo, Rabinowitz, and the crisis of Eris. The IAU vote. The New Horizons launch. The flyby. The year-long return of data. The continuing analysis. The possibility of an orbiter someday. A small world far from the sun became a thread connecting more than a century of astronomy. New Horizons answered all the questions he couldn't ask and revealed a world more interesting than anyone who knew the moving that in his photographs could have suspected. A final way to understand Pluto is to separate three different Plutos. There is the cultural Pluto, the ninth planet, the underdog, the small distant world people defended because it felt familiar and beloved. That Pluto matters because science is done by human beings, and human beings care about stories and names. There is the dynamical Pluto, a resonant Kuiper Belt dwarf planet, controlled by Neptune's migration history, sharing an orbital region with many other icy bodies, unable to clear its neighborhood but important as the prototype of a population. That Pluto matters because it teaches the architecture of the solar system. And there is the physical Pluto, a rounded world with mountains, glaciers, haze, red organic chemistry, a large moon, small tumbling moons, volatile cycles, and possibly a deep internal ocean. That Pluto matters because it is a real place. The mistake is to make one Pluto erase the others. The best understanding holds all three at once. The category it inhabits matters less than what it is. And what it is, it turns out, is extraordinary. The most interesting thing about Pluto may be that every attempt to make it smaller has made it larger. It was supposed to be Planet X, then turned out to be too small. That made it stranger. It was supposed to be the ninth planet, then became a dwarf planet. That placed it in a population and made the outer solar system richer. It was expected by many to be a cold, inert leftover. New Horizons revealed mountains, glaciers, haze, chemistry, moons, convection, and possible clues to an internal ocean. Pluto keeps escaping the simple version. Maybe that is why people reacted so strongly to its reclassification. The public felt a loss before the science had time to offer the replacement. But the replacement is better. A lonely ninth planet at the edge of a simple diagram is interesting. A complex dwarf planet at the inner edge of a vast Kuiper Belt, with a binary moon system, volatile glaciers, and a role in the history of planetary classification, is more interesting. The lesson is not that names do not matter. Names do matter. Categories matter because they guide attention. But a category should help us see more, not less. If calling Pluto a dwarf planet makes us remember the Kuiper Belt, the population of icy worlds beyond Neptune, and the way planetary systems form from leftover material, then the category is useful. If the word planet helps us recognize Pluto as a complex world with geology and atmosphere, that perspective is useful too. Pluto sits at the intersection of those meanings. It is dynamically a dwarf planet. Geologically, it is a world. Historically, it is the planet many people lost. Scientifically, it is one of the best reminders that the solar system is still capable of surprise. There is also a useful emotional rhythm in Pluto's story for a sleep audience. The beginning has curiosity, a faint moving point on a photographic plate. The middle has conflict, the planet's status, the discovery of the Kuiper Belt, the discomfort of changing a familiar map. The scientific climax has revelation, New Horizons turning a dot into mountains, glaciers, haze, and a heart-shaped nitrogen plane. The ending has calm, Pluto remaining itself, regardless of the argument around it. That rhythm works because it mirrors the way science often feels from the inside. First something is noticed, then the old explanation strains, then the category changes, then the object becomes more real, not less. The discomfort is temporary. The larger understanding remains. Pluto is a gentle way to tell that story because no one is harmed by the change. A word changed. A world remained. And when the world was finally seen, It rewarded the attention with beauty and complexity. This is why the final message should not be bitterness about demotion. It should be gratitude for revision. The old 9-planet solar system was easy to remember. The modern solar system is harder to fit on a classroom poster, but it is more honest, more crowded, more dynamic, and more alive with different kinds of worlds. Pluto did not disappear from the solar system. It helped reveal the solar system as it really is. The more one looks at Pluto, the less useful it becomes as a symbol of loss. It is better as a symbol of scale. A small body can have a large story. A distant object can become central to how we classify worlds. A faint dot can reorder a map. A flyby lasting only hours can produce decades of scientific work. A body smaller than the moon can hold mountains taller than many on Earth, glaciers of nitrogen, a thin blue atmosphere, and a companion system shaped by an ancient collision. That combination is exactly what keeps the subject interesting through a long script. Pluto contains history, controversy, mission drama, visual surprise, and genuine planetary science. It offers names a viewer remembers and facts a viewer may not expect. It begins familiar and becomes strange. That is a strong structure for retention. And there is another quiet point. Pluto teaches humility. We argued about its label before we understood its surface. We placed it in a list before we knew its family. We imagined an edge before discovering a belt. We thought the outer solar system was sparse before learning how populated it is. Again and again, Pluto showed that the map was not finished. That is one of the most useful feelings astronomy can give. The sense that even familiar names can still open onto unknown places. For the listener, Pluto should feel both distant and understandable. Distant because it lives in a region where sunlight is weak, years last centuries, and water behaves like rock. Understandable because its story follows patterns we know: discovery, mistake, revision, travel, arrival, surprise. That balance is important. If Pluto is only alien, it becomes abstract. If it is only familiar, it loses its power. The best version holds both. A world can be made of strange ices and still have landscapes we can imagine. It can be too cold for ordinary experience and still have seasons. It can be smaller than the moon and still carry enough complexity for a spacecraft to transform an entire field of study. This is why the episode should not rush past the details. The details are the reward. The blink comparator, Charon's discovery, Eris forcing the question, the flyby sequence, Sputnik Planitia, the blue haze, the red pole of Charon, Erikatha's gentle contact binary shape, Tombaugh's ashes leaving the solar system. Each detail gives the listener another reason to keep following. Pluto is not just one idea. It is a chain of good ideas connected by one small world. The calmness of the topic comes from that slow chain. Nothing in Pluto's story happens quickly by human standards except the flyby itself. Tombaugh's search took patience. Pluto's orbit takes centuries. Its seasons unfold over generations. Its nitrogen ice moves slowly. Its atmosphere changes gradually. New Horizons spent most of a decade crossing the outer solar system and then more than a year sending the encounter home. Even the debate about classification has not ended. It continues quietly in language, textbooks, lectures, and public memory. That pace suits the channel. Pluto is not loud. It is persistent. It waits in the dark, and the more carefully we look, the more it gives back. And perhaps that is the most respectful way to tell the story, not as a courtroom case over whether Pluto deserves a title, but as a slow unveiling. A dot became a planet became a problem, the problem became a population, and the population became a new region of the solar system. Then a spacecraft arrived and showed that the most controversial object in the classroom diagram was also one of the most visually and scientifically surprising worlds we had ever visited. That is a good shape for memory. It lets the viewer keep the emotional Pluto and gain the scientific Pluto at the same time. Nothing beloved has to be erased. It only has to be placed in a larger and more accurate sky. The result is softer than an argument and stronger than nostalgia. Pluto remains loved, but now for better reasons. A small world, a bigger map, and a lesson that science can change the label while deepening the wonder. And when New Horizons looked back across that distance, the answer was not simple, but it was beautiful. This is why Pluto remains such a strong subject for a quiet space episode. It begins with an argument everyone can understand. Is Pluto a planet or not? But it leads to something deeper than the argument. It leads to discovery methods, orbital resonances, icy geology, volatile climate, spacecraft design, Kuiper Belt formation, human memory, and the way science changes familiar categories without destroying wonder. A listener can enter through nostalgia and leave with a larger solar system. That is the ideal result. Not to win an argument about a word, but to make the world behind the word more vivid. Good night.